All right, today I'm going to cover sampling distributions. Typically in statistics, we talk in terms of samples so that we can make inferences about the population. And when we talk about samples versus population, we can use a statistic versus a parameter. A statistic is used in a sample, and a parameter is something that describes a population. The nice thing about this is that P and for parameter and population, they both start with the same letter. And statistic and sample both start with the same letter. And so when I'm talking about a statistic, that refers to a sample. When I'm talking about a parameter, that refers to the population. We have covered notation in terms of mu and sigma. Mu means the population mean, population average. Sigma is the population standard deviation. And x bar is the average of the sample, while s is the standard deviation of the sample. When we're talking about statistical inference, we are generally collecting data from a sample, and then we make a generalization about the population based on that. And when we do this, we are referring to a specific sampling distribution based on all the different possibilities that might arise from the statistics that we're using or from the population that we are examining. The law of large numbers we've talked about in probability, but just means that the more times, the more observations that we draw at random, as the number of observations increase, we get closer and closer to the actual true value of the population. When we discuss sampling distributions, it's important to recognize that a sampling distribution is a distribution of its own. It's not just one specific value. We have the population distribution, which is all of the values that the variable can take on in the population. And then we have the sampling distribution of a statistic, which is all of the different samples that you could take of a certain size from the population. So let's say my population has 100 people in it, and I draw a sample of size 4. There's a huge number of samples of size 4 that I could take from my population of 100. So I could take the first 4 people, I could take the last 4 people, I could take the first, the 25th, and the 50th, and so on. So you have to think about how all of those populations can come about, and that describes, when we put that all together, that is what we call our sampling distribution. So let's say we have our population distribution here, where we're talking about 100 of the color blue and 100 of the color red, and our parameter is split at 50%. I could take a sample of size 20, and in that sample, I could get more blue than I get red. I could get more red than I get blue. I could get a lot more red than I get blue. There's a bunch of different ways that my distribution could look. And when I did my first sample, talking about the distribution of red, I had 8, which was 40%. That occurred. Here, I had 11, which was 55%. Here, I had 13, which was 65%. And this p hat is used to represent the sampling proportion, where we have P, which represents the population proportion. So all of these different values and the ways that they can occur create our sampling distribution. The sampling distribution has specific values as well. We have a mean and a standard deviation of the sample. We have x bar, which would mean that we are taking the average of our certain sample. And then our standard deviation. Because our standard deviation is not as variable as our population, we want to adjust. So we have the standard deviation divided by the square root of n. The mean of the statistic is always equal to the mean of the population. So the average is always the average, and we call that an unbiased estimator. In any particular sample, the mean may fall above or below the population mean, x bar may, but in general, our x bar is an unbiased estimator of mu. So if we want to know what our mean is, we estimate that it is the population mean. For our standard deviation, we then divide that by the square root of n. So let's say I have a population of 25 people. I take a sample of size 10, and I get different x bar values. We know that our average is 25, so our distribution is going to be centered at 25, our sampling distribution, but our standard deviation is going to be a little bit different. Because the standard deviation of the sampling distribution is sigma over root n, the averages are less variable than the individual observations, and averages are less variable than the results of small samples. So while the standard deviation of the distribution of x bar gets smaller, it does so at the rate of root n, not n. So to cut a sampling distribution's standard deviation in half, you have to take a sample 4 times as large, not just twice as large. So when you're trying to figure out how to reduce variability or what increases variability, you have to think about the sample size that you're dealing with. Large samples are less variable than the results of small samples. So when I take a sample of size 4, I could get a wide range of values. But if I take a sample of size 100, I'm going to have smaller variability. Part 3 of this, we described center, which is our average, variability, which would be sigma over root n. If the distribution is normal, then so is the sampling distribution. This comes into our conditions. It's going to be important when we're talking about whether we can whether we can perform normal calculations. If our distribution is normal, we can perform normal calculations. And there's a couple of different ways that our distribution can be considered normal. One way is if the population itself is normal. So if the population itself is normal, then the sample will also be normal with a mean of mu and a standard deviation of sigma over root n. If the population is not normal, we can apply the central limit theorem. The central limit theorem says that if our sample size is relatively large, it will also follow a normal distribution. So as sample size increases, the sample means change its shape and it becomes more and more normal. So the important thing here is if your sample size is large enough, we can use normal approximations. Well, what do we consider large enough? 30 has been seen to be a good number. So if our sample size of n is greater than 30, then the central limit theorem applies and we can perform normal calculations. Even if the distribution is not normal, as long as our sample size is large enough, we're okay. So based on service records for the past year, a technician requires complete preventative maintenance on an air conditioner. There's a strong right skew distribution. The mean is 1 and the standard deviation is 1 as well. We're going to take a simple random sample of 70. So it does not matter that the distribution is strongly right skewed. Because the sample is larger than 30, we can use the central limit theorem and perform normal calculations. So now we have our mean as the mean, and our standard deviation be 1 divided by the square root of the sample size. And then we can perform our normal calculations using normal CDF or the tables. So we have our z-score, probability, and normal calculations are all set to go. If we're talking about statistically significant, you have to look at the sampling distribution of the sample mean. Any statistic we calculate from a sample will have a sampling distribution. So whether we're determining whether something is statistically significant or not is what is the likelihood that this would happen by chance alone. If an observed effect is so large that it would rarely occur by chance, it is called statistically significant. So this is like smelling Parkinson's disease when we got 0 out of 32. That's pretty statistically significant, that none of that, there was 0% of that it could have happened by chance alone. We are going to use the mean of mu and standard deviation of sigma over root n a lot. It's really important to remember the central limit theorem. If n is greater than 30, we can use normal calculations, or if the population is normal. Those are 2 stipulations. And I will show you some fancy calculator tricks later in the next slides.